In this video we will explain about open loop gain in a process control system. The explanation starts with a bare minimum system to emphasize the effect of controller gain, and eliminate other contributing parameters. Here is an example of a simple open loop control system. Its main purpose is to provide correctly chlorinated water supply to the user, by dosing chlorine into the main pipeline proportional to the water flow. If the chlorine dosage is inadequate, then there could be some germs left in the water. On the other hand, too much chlorine could be dangerous for water users and increase corrosion rate of the pipeline, beside increased material costs. To avoid complication, let's assume that the system has been perfectly designed so that capacities of water supply and chlorine supply are perfectly balanced, and the control valve to determine the chlorine flow is perfectly linear. Water usage can't be predicted in advance, but never exceed the water supply capacity. Let's put some numbers to give us some quantizable picture. The span of water flow meter is between 0 to 100 ton per hour. The chlorine flow is proportional to opening of the control valve, which can vary from 0 to 100 gram per hour. To calculate controller gain, both input and output parameters must be scaled to between 0 and 100% first before taking the ratio. In this example, the engineering unit can be simply replaced with %, hence reducing the calculation load. Let's start the simulation using a spreadsheet. When the control gain is 1, the curve of process value and control output are overlapping. The chlorine concentration in the water for user is maintained at around 1 part per million. Note that in this case, the control direction is direct acting. It means that any increase in process value is responded by increase in controller output. When the control gain is reduced to just a half, the curve of control output is also reduced by a half. The chlorine concentration in the water for user is maintained at around a half ppm. When the control gain is increased to 2, the curve of control output is also increased by twice as process value. The chlorine concentration in the water for user should be maintained at around 2 ppm. But remember that the controller output is physically limited to 100%. Thus, the formula for controller output must be modified to accommodate this limitation. But this implies that the chlorine concentration cannot be maintained at 2 parts per million, especially at higher water flow rate. In this example, when the water flow is 70 tons per hour, the chlorine concentration would drop to only around 1.4 part per million. If the goal is to maintain the concentration of chlorinated water at 2 parts per million, we can limit the water flow rate at 50 ton per hour. It can be done by adding a flow restriction orifice to the water pipeline. As we can see in the graph, the chlorine concentration of the water outlet can be maintained. If we don't want to reduce the system capacity, we need to increase the chlorine supply capacity to 200 gram per hour in order to keep the chlorine concentration at the water outlet at 2 parts per million. Note that in the table, the control gain is 1, since ratio between % output and % input of the controller is 1. 100% of controller's output now corresponds to 200 gram per hour. From the explanation just now, we can learn some lessons from controllers with open loop gain. First, it introduces problems of oversized and undersized measuring and actuating devices. These problems exist for any type of controller, and not limited to this one only. We will address this in a future video. Next lesson is that controller with open loop gain can respond to change in load. It means that the change is initiated by the user or customer of the system. In this case, change in water flow rate can be responded to maintain chlorine concentration. Another lesson is that the controller can't respond to change in disturbance. It means that the change is unintentional or unpreferred. For example, when the chlorine supply pressure drops due to temperature change in the environment, nonlinearity of the control valve, pipeline clogging, or the storage tank is depleted. This problem can be addressed by implementing a closed-loop process control system, which will be explained in the next video.